All right, so what I want to do is I want to talk about some of the more common distributions. I want to give you a sense of how you would come across distributions. So I have two carefully prepared envelopes. These are not trick envelopes. My son actually does have trick envelopes. I need two people who can volunteer. So, excellent. So one envelope has twice as much money as the other. I need each of you to choose an envelope. Did you? Okay. Don't open them yet. Can you pass them back? Keep them straight. All right? So we're going to put the guest on the spot. What's your name?
Cameron.
Cameron with a C?
Yes.
Excellent. So that's the name of my son, so you have extra credit. You are excused from all homework for the rest of the semester with full credit. All right? Let's look at everything from Cameron's point of view. Should Cameron open the envelope and take the money in that, or should he switch with his brother? I'm assuming this is your brother. This doesn't look like a difficult assumption. Okay. Should he switch envelopes or should he hold? What do you think? And he's not allowed to open the envelope. Switch. Why? So let's calculate the expected value. How much money do you think he has in his envelope right now? X. Right. Whenever you don't know something in mathematics, what's the answer? X. What percent of the time is this going to be the maximum of the two values? And what percent of the time is it going to be the lower? So if he stays, we expect X. If he switches, half the time, how much should he have? X over 2. And the other half of the time, how much should he have? 2x. Well, a half times 2 is x, so this is already greater than x. It's going to be 5/4 x. So what should you do, Cameron? So switch. But then you realize you should apply this argument again, right? And so how much do you have in your envelope right now?
5/4 x.
Nope, you have y. So if you keep it, how much will you have? And if you switch, 1/2 y plus 1/2 2y, what should you do?
Switch.
Okay, switch. So this could go on all day. How long is the class supposed to be? I got it wrong when I was filling in for Professor DeVoe. It's 50 minutes. So we can do this for a long time. Eventually, something should happen. We should realize that this is absurd. We should not be spending all of our time switching back and forth. What's going on here? What's wrong? Yes?
We're allowing the total money in the system today. We're not accounting for that.
In what sense? I mean, I've done the calculation. It makes sense to switch. So you guys can keep switching as we do this. I mean, switch as much as you want, so you no longer know.
X plus X should be not what it is.
Shouldn't it be x and 2x, or x over 2 and x? Yeah, shouldn't it be x and 2x?
We don't know.
Because otherwise it's 4 times. Yeah, that's twice as much. Shouldn't it be x and 2x?
For this one?
For switching.
Well, he says x over here, and then half the time he has half the money in the envelope, and the other half of the time he has twice as much money.
That wasn't the problem. Oh, okay.
I told you one envelope has twice as much as the other.
And that one envelope has 4 times as much.
Which envelope has 4 times as much?
It should be x over 2 and x in parentheses rather than x over 2 and 2x. Or if you want to have the
X is the smaller amount of money, not the amount of money it starts with. Yeah, but they don't know.
I'm not comparing this envelope to these envelopes. These ones I agree differ by 4. I'm comparing this amount to this amount, this amount to this amount.
When you say x over 2, x is a different constant than when you say 2x. So you're using 2 different values for x.
Close. What are we assuming about x over here initially? It's a constant, but where am I drawing this constant from? I'm putting money in these envelopes. Not my own money. I'm charging this to Williams. Where am I getting this money? If I tell you there's,
Oh, because you're like.
if I tell you there's $10 in the envelope, do you think $5 and $20 are both likely for the other envelope? If I tell you there's $1 million in one of the envelopes, do you think it's more or less likely that I have 500,000 or $2 million? This is trying to put a uniform distribution on the entire real line. Can you put a uniform distribution on the whole real line? No. I can't assume that all numbers are equally likely. So one of the biggest difficulties in probability is figuring out what is the correct model for what you're studying. This is why we're spending so much time learning all these different distributions. This is not surprisingly called the two-envelope problem. We're really good at names. Two-envelope problem. And the difficulty is we cannot put a uniform distribution on the entire real line. And so the assumption that these are both equally likely for a given value of x, that's not the case. So are you happy with your envelope? Or do you want to switch again?
I'm happy.
All right, do you want to open it up and see if you won?
Yeah.
And what's his chance of winning? Half. It's got to be 50% by symmetry. So did you get x or 2x?
I got X.
Okay, you got x. So you should have switched. So the whole point is we want to get a sense of which distributions can we look at. So what's going on here in the background is the uniform distribution. And we'll say x is uniform 0, 1. Well, let's do more generally AB. If the density of x is equal to 1 over b minus a less than equal to x less than equal to b, and 0 otherwise. So this will integrate to 1. It's non-negative, so this will be a probability distribution. Okay, what's the most common choices of AB? The most common choice is 0, 1. It's choosing a uniform number on 0, 1. We had a homework problem on the inverse CDF method where if we can generate something from the uniform on 0, 1, if we have a nice formula for the inverse CDF, we can actually generate other random variables just from knowing how to generate uniforms. This is one of the most important ones. What do you think the expected value of x would be? We want to calculate the expected value of x. Yes?
X over b minus a.
Well, the final answer can only involve a and b, right? Because we integrate out x. This is going to be the integral from a to b of x times 1 over b minus a.
So that's what the integral is.
Oh, I see. Yes, yes. And what is the value of that?
The mean of
Yeah, the mean of b. So when you of a and b, the number halfway between. Because the distribution is so symmetric, it's got to be halfway between. If you don't see this, what could you do? If you don't see that it's b plus a over 2, what should you do? Just do the integral. If we want to calculate the variance, we would now integrate x squared and then subtract the square of the mean. Or conversely, what we could do is we could integrate x minus b plus a over 2, square that, and integrate. I'd much rather integrate x squared. Okay, so what's looking on in the background here, what we're using for a lot of these problems is nice formulas for the variance. So I don't think we've done the variance formulas yet. Is that correct? We haven't done the variance formulas? Okay, so we want to use formulas for variance. And so the expected value of x minus mu squared is the variance. And so if we expand things out, this is the expected value of x squared minus 2 mu x plus mu squared. And so now we have a nice expression like this. What do we do to analyze this expression? How would we analyze this expression? Yes? Linearity of expectation. The expected value of the sum is the sum of the expected values. And so if we do that, now we have 3 terms. we have the expected value of x squared minus twice the expected value of mu x, and then plus the expected value of mu squared. So when we use linearity of expected value terms, I claim something nice is going to happen in several of them. I do not want to go all the way back to the definition and write out what these are in terms of integrals and sums. I want to just look at them at a higher level. Here is a new random variable. No matter what the distribution of x is, I always return the value of mu squared. What's the expected value of this random variable? Mu squared. Just no matter what happens, you always get back mu squared. For this one, I take x and I always multiply it by this fixed constant 2 mu. So what should I get back for the expected value of this? 2 mu times the expected value of x. I can pull the 2 mu outside, and the expected value of x is just mu. And over here, well, this is just the second moment. It's just the expected value of x squared. So we get the expected value of x squared minus twice mu expected value of x plus mu squared. 2 mu squared plus mu squared becomes a minus mu squared, and we're left with the expected value of x squared minus mu squared. Or if you want, you can rewrite this as the expected value of x squared minus the expected value of x squared. This is a really good formula for the variance. It allows you to compute the variance in terms of the pure moments, the first moment, the second moment, rather than having to expand things out. Depending on what you're given, sometimes one expression is more convenient than the other. I'm going to risk going back to Math 150. How many of you vaguely remember directional derivatives? At least the phrase directional derivatives. There's two ways to calculate directional derivatives. There's the formal definition, and then there's a really nice dot product with the gradient. You don't want to go back to the formal definition. You want to just take the dot product. That's the faster way of doing the calculations. It's the same thing here. For many of these calculations, this is the simpler way to do it. The next expression we want to do is we want to talk about the variance of sums. Now we have the expected value of a sum is the sum of the expected values. This is sadly not always the case for variances. So we'll start off with a nice lemma. If x and y are independent, then the expected value of xy is the expected value of x, expected value of y. This seems to make sense. If x and y don't, if knowledge of one gives you no information about knowledge of the other, then the expected value of the product should just be the product of the expected values. Let's think about how we would do this. So let's let z be the variable x times y. So the expected value of z would just be the integral from minus infinity to infinity z times the density of z dz. But now we want to rewrite this in terms of the joint density function. So if we want to rewrite this in terms of the joint density function, you'd be integrating from minus infinity to infinity. And now we want to think, how do we want to write this? So if I want a given value of the product, I can let, here z goes from minus, I can let x go from minus infinity to infinity. If I give you a value of x, what should my value of y be?
Z over x.
Z over x, not minus. Dx dz. Okay? So now we have an integral to do. When you see this, what would you like to do? Split them up. And we know the joint density function does that this is going to just be the density function of x times the density function of y at z over x. And so this suggests a change of variables. What would we like to replace z over x with? Y. So can I replace z over x with y right here? Why not?
So you're integrating over z.
I'm integrating over z and I'm integrating over x. I want to change the z integral to a y integral. But here I integrate out all the x's first. I've got to be careful. I can't write y as z over x because I've integrated out the x. What do I need to do? Yes?
Flip the order.
I need to flip the order of integration. This is one of the only things we know how to do for multivariable calculus. Right? Almost everything else seems to have been wiped from our memories. Interchanging orders of integration is one of the few survivors. Alright? So x goes from minus infinity to infinity. Integral z goes from minus infinity to infinity. Z fx of x, fy of z over x, dz dx. And now if we let y equals z over x, let's see what would happen. Okay. So now, let's let y equal z over x. What would dy be?
One over x.
Over
dz.
1 over x dz.
plus minus 1.
I'm sorry?
Forgetting calculus.
Okay. So x is a constant here. So now if we substitute in, is this going to work? Yes.
Why did we start with x and z instead of just x and y?
Because I wanted to get something by you.
I'm sorry.
I was trying to slip something by you to just see how easy it is. You're absolutely correct. There is a mistake here. Nobody noticed it over here. If we now continue this argument, we have dy is 1 over x dz. So then that means dz is x dy. So when we put this into the integration, we get the expected value of z is going to be the integral x goes from minus infinity to infinity, integral y goes from minus infinity to infinity, and now z is equal to yx, and now we have fx of x, fy of y, dz, dy is 1 over x dz, so z was xy, and now we have dz which replaces x dy, and when we move this over here, we have x squared. Something is wrong here. What I want you to see is I want you to see how easy it is to make a mistake. What does this look a lot like? The quantities we're doing looks a lot like what? So somebody said this before, and then they corrected themselves because it was not the right thing. They said not z over x, they said what?
Y.
Z minus x.
Z minus x. Why did you say z minus x?
No, I didn't say it.
Oh, okay. Well, okay. Why do you think they said z minus x?
Because the last time we did the mixing variables, it was Z minus
When we did mixing variables, when we did additive stuff. We had a z minus x. We did an additive convolution. This is in theme with the envelope problem. The whole point today is to try to sneak as many things past you. It's really easy. These are, yes?
Is it because in the additive problem, we went to the CDF, and then when we took derivative, the derivative of c minus x was 1. But here we have to take derivative and it's 1 over x. So
There's going to be an extra 1 over x coming here when we're trying to do a multiplicative convolution. And so what we were doing here is we were trying to write things additively. And then we said, oh, well, it's got to be 0 over x, but then we did the rest of it in the same way. What I want to do is I really want to spend time trying to figure out how we should set things up like this. So let's go backwards a little bit. Do you remember how we formed the convolution? How do we get the convolution? Why was the additive convolution, x plus y? Why was its density the integral of f of x, f of t, f of x minus t? Where did that come from? How do we prove that? If you think that this isn't that big of a deal, this is what led to the financial collapse. Okay? In 2008, there were people who were using formulas for mathematics in places without checking to see if the conditions were met. They were applying formulas in slightly different settings. It just follows naturally. It just follows the same way. We've got this extra factor of an x now. We've got to figure out where is this coming from. I can go through all the different standard definitions and all the standard examples from there. You can read that. I want to really emphasize, how do you find things? Where did the convolution come from?
Did we have to multiply by dz of z of x when we turned y into z of x?
All right, so let's go back and review where the additive stuff came from. So let's go back to the additive case. So we had here z was x plus y. And we could look at the probability that big Z was at most little z. This was the integral x goes from minus infinity to infinity, and then the integral y goes from minus infinity to how far?
c minus x.
To z minus x. And then we had the joint density function of xy dy dx. And this was big F of z. And then when we looked at this, this was the integral x goes from minus infinity to infinity. And then we were, let's say we're in this place where we had independent random variables, so this split, and this was fx of x, fy of y. So we then got fx at x, and we had the antiderivative of y at z minus x minus the antiderivative of y at negative infinity times dx. What's the cumulative distribution function at negative infinity? Zero. So this is just 0. And now this was the cumulative distribution function. So this is going to lead into what we're going to do after this, the CDF method. How did we go from the cumulative distribution function to the density? We took the derivative. And so we now have the derivative of this. Can we pass the derivative through the integral sign?
Yes.
Yes. Why? What class? Real analysis. If you haven't taken it, please do so. Preferably by Monday. Right? If we take that, we can then justify passing the derivative inside. And this is one of the most important ideas in probability. Integration is hard. Typically, if I give you a density function, we can't calculate its CDF. But we're going to calculate the CDF by integrating, and then we're going to immediately differentiate. And when we immediately differentiate, we come back to where we started. Negative infinity to infinity, fx of x, the derivative of big F of y is little fy of z minus x. And now we're taking the derivative with respect to z. d by dz of z minus x. I am doing this as an overkill. What's the derivative of z minus x? 1. 1. All right, let's try to go now to the product situation. So now we're going to write things as a product and see what we get. All right. So now we will have z equals x, y. Let's assume x and y are greater than or equal to 0. Okay? Let's just make my life a little bit easy. I want to calculate the probability that z is at most little z. So x is going from 0 to infinity. And what can you tell me about y? What will y go from? 0 to z over x. And now we'll have f(x) of x, fy of y, dy dx. Notice there's a little bit of a difference here than what we had before. In what we were doing over here, we had a z minus x over here. So when we take the derivative, it's not going to be a big deal. But in the other one, the issue now is we have a z over x. So when we take derivatives, that could cause some problems. It could cause something to be a little bit different. Okay? So now, we get f z of z is the integral x goes from 0 to infinity. When we do the y integral, what do we get when we do the y integral?
Capital F.
Capital F of y at z over x, lower, sorry, that's it, now, I guess I should include the minus the cumulative distribution function at 0, but since we're looking at continuous random variables, what's the cumulative distribution function at the very beginning?
0.
0. So this part vanishes as well. Now to find the density, we take the derivative. Again, take real analysis to justify passing the derivative inside. We get fx of x. What's the derivative of big F of y at z over x with respect to z?
Small f of z over x times
Small f sub y. And where do I evaluate it?
Z over x.
Z over x. And now I need d by dz of z over x.
1 over x.
And what's d by dz of z over x? It's a 1 over x. Slightly different. The multiplicative convolution has this extra factor of 1 over x. If we come back to what we were doing before, did I have to erase it? I think I did have to erase it. Oh well. When we were doing all of this, I think it was somewhere on this part of the board, what were we off by? We were off by a factor of
1 over x.
either x or 1 over x, depending on how you want to do it. We had an extra factor of x. We had x squared y, not xy. The reason is we wrote down the wrong formula here for the multiplicative convolution. We wrote down the wrong formula for the joint density. We should have a 1 over x here. And if you put that in, then everything will go through and it will split, and you'll get the expected value of the product is the product of the expected values. So I want you to go through and do that calculation carefully at home. Yes.
So
Hopefully that was the only mistake I was trying to make. Hopefully I'm not making another one.
So the big F is the cumulative distribution function.
The
and
big F is always cumulative distribution function. It's the antiderivative.
And then the little f is the expected value.
No, the little f is the density.
Okay. So that little f right there, that
Right. This will be the density, and the density differs from what we thought by it has an extra factor of 1 over x. And so it's really easy to take these expressions and slightly misapply them. To take something that you think works and just move it over to another setting. This is why the best thing is always to go back to the definition. This is why the CDF method, I never memorize it. I always rederive it from scratch every single time I need it, because this is the only way I know I'm not going to drop one of these factors. What's really lurking in the background, and I'm not going to go into too much detail because it requires which class? No.
Complex analysis.
No.
Abstract.
Which class do I seem to avoid like the plague in this class, even though it's a prerequisite? No.
Linear.
Not linear.
Statistics.
What class have you forgotten almost all of your material? Multivariable calculus, right? How many of you have seen the chain rule? How many of you have seen the change of variable formula? How many of you remember the change of variable formula? That's what you really want to be going on in all these calculations in the background. All right. So what I want to do is I want to now apply the CDF method and show us how we can pass from knowledge of one random variable to another. What we were doing here was a product. I want to go back now, so it's called the CDF method. I want to do the same example that's in the book. I think it's y. Okay, so x is going to be uniform on 0, 2, and y is going to be x squared. So the idea is, if I understand the random variable x, I should understand the random variable y. There's a very nice relationship between the two of them. The first question to ask is, well, what is the density function of y? We know the density function of x. Fx of x is equal to 1/2, 0 less than x less than equal to 2, and it's 0 otherwise. Okay? So now, let's calculate the density of y. How do we calculate the density function of y?
Start with the CDF of y.
Start with the CDF. So the CDF of y, it's the probability, and I always like writing it very long way, the probability that big Y is less than equal to little y. Well, this is going to be the same as the probability that x squared is less than equal to y. So I want to convert a condition on x squared to a condition on x. If instead I had y was the exponential of x, I would want to convert from a condition on the exponential of x to a condition on x. What does it mean for x squared to be less than equal to y? I'm sorry?
X is less than root of y?
No.
No?
What does it mean if x squared is less than equal to y?
X is greater than negative square root of y.
Good. We'll then immediately get to what was just suggested. We get this is the probability that negative square root of y is less than equal to x is less than equal to the square root of y. For this particular problem, do I have to worry about negative values of x? No. X is non-negative. So this probability is the same as the probability that x is less than equal to the square root of y. But again, it's very easy to accidentally make mistakes to drop things out. At the end of the day, if I had given you a random variable that had some negative probabilities, you could see that you've made a mistake by your final result for the PDF of y. What should it integrate to? 1. If it doesn't integrate to 1, you've made a mistake somewhere and you've missed something. What's the probability that x is less than equal to the square root of y?
Big F of root y.
So it's big F of x at square root of y. So now there's two ways to go about this. One is we actually know what the CDF of f of x is. We could evaluate the CDF and then take its derivative. I see no point in integrating to then immediately take the derivative. Right? There's more than enough material to do today. Why should I integrate it if I'm going to immediately differentiate? Let's just differentiate. This is the cumulative distribution function of y, so the density of y is just take the derivative. And it's going to be the density of x at square root of y. Is that correct? What am I missing? Chain rule, right? I then have to take the derivative of the inside. I have big F of x at square root of y. So it's the derivative of big F of x times the derivative of square root of y. And the derivative of square root of y is 1/2 1 over square root of y. We've got to be a little bit careful. There's one more thing to be careful about. Does this hold for all values of y? So what values of y does this hold for? Yes.
Not equal to 0.
Not equal to 0. A little bit more than not equal to 0. It's a good start.
Negative, less than equal to 0.
So you're saying that this is true for 0 less than equal to y.
0 less than 1.
That's the one.
Oh, come on. We're not going to argue over 1. Fine. Take away the... Anything else? We've now got 0 less than y. Is this the density of y?
Y has to be less than 4.
Good. Y has to be less than 4. Because y is x squared. The largest x can be is 2. So the largest x squared can be is 4. This is why I did not want to choose a uniform on 0, 1. If I choose a uniform on 0, 1, the upper bound is the same for x and y. I want to see a little bit of a difference, a little bit of a variation. So when we look at what's going on now, over here, we should be very careful. It is the cumulative distribution function of x evaluated square root of y. That's true. That's by definition. But if I then want to take the derivative of this and actually plug in some various things, I've got to be a little bit careful. Well, fortunately my density function will be 0 if I take square root of y outside of 0 to 2. What I want to do now is I want to simplify and I want to put in what the density function of x is at the square root of y. So what's the density function of x at the square root of y? What would that be? It would just be a half. So we get the density function of y at square root of y is going to be equal to a half. Great, so we get a 1 over 4 square roots of y, 0 less than y less than equal to 4, and 0 otherwise. Yes?
Sorry, why are we looking at the density function of y at the square root of y?
Oh, sorry.
Okay.
Sorry, you're right. We're not. That's not a mistake I meant to make today. Do you believe the answer? What's a good property this answer has?
Integrates to 1?
It integrates to 1. So if you do the calculation, we have a y to the negative 1/2. When you integrate it, we get a y to the positive 1/2 divided by a half. The 2 will come upstairs. Let's make it 1/2. It'll all work out. Excellent. It integrates to 1. Anything else? Anything else good about it?
It's always positive.
It's always positive. Positive / non-negative. This is not a proof that we haven't made a mistake. But it's at least 2 good points in its favor. There's something fascinating about this density. This density is blowing up as y goes to 0. We started with a really nice random variable, a uniform random variable, and we squared it. And see how bad the density became. Don't expect densities to stay nice as you do things to them. This is one of the reasons why we care so much about the central limit theorem, is it tells us that to an incredible degree of precision, you can approximate really bad things with normal curves if you're adding a lot of independent random variables with nice distributions. For many purposes, you don't need to know exactly what's going on, you just need to be close. Okay, any questions about the CDF method? Yes,
How are we making sure that it's always positive?
just by inspection.
Okay.
You know, we know y is between 0 and 4, so if I just plug in here, this is always going to be positive. Okay? It is extremely easy to make mistakes like this. The best way I know is to just keep writing things down very, very carefully. When you try to do shortcuts, you will make mistakes with high probability. If you go through the CDF method, it's more cumbersome, it's longer. But you are more likely not to skip something and not to accidentally assume something. The other thing is, don't do things you don't need to do. Don't find the antiderivatives unless you really need the antiderivative. Okay, any questions about this part? Alright. So the swivel check. Oh, okay. The battery has failed again. All right. Not today. Okay. So let's go back to the original thing that was motivating all of this. The expected value of a product is the product of the expected values. So the proof of this is in the book. We've talked about how you prove this. Let's look at consequences of this. Let's say x1, xn are independent random variables. Then the big result is the variance of their sum is the sum of the variances. More is true. If we look at the variance of a1 x1 plus an xn, that should be something variance of x1 plus something variance of xn. So you should know the answer from your reading, but I want to try to guess what's reasonable. Any thoughts as to what should go in front of the variance of x1? What should go in front of this?
A1 squared.
A1 squared. Why not just A1? Why A1 squared?
Is variance a square for whatever reason?
Well, variance is square. Variance is non-negative. If I just have the x1 term, I shouldn't be getting something that's negative. If A1 were negative, if I just had an A1 here, I know the formula can't be right. Variance involves squaring things, so I don't think it's going to be an absolute value of A1. I think a square of A1 is a very natural thing. If I double x1, the variance should increase by a factor of 4. And so more generally, we have a formula like this. Okay? So the way you prove this is precisely the same as what we did here. We do things just by brute force algebra. Okay? I'll do just the special case where we have the variance of a sum of two terms. The argument in general is going to be identical. So let's say we want to calculate the variance of x plus y. So there's a lot of ways to look at this. One way is that this is the expected value of x plus y minus the mean of x plus the mean of y squared. Yeah, this is the definition. And if I expand things out, what will I get? I'll get the expected value of x plus y squared minus twice x plus y mu x plus mu y plus mu x plus mu y squared. Well, some of this is nice. The expected value of this whole thing is the sum of the expected values. And there's many ways of doing the algebra. I'll just do it by brute force. So this becomes the expected value of x squared plus xy plus y squared minus twice, what's the expected value of x plus y? Expected value of x plus expected value of y, so we'll get a mu x plus mu y squared, and then a plus mu x plus mu y squared.
Should it be 2x y?
Yes, it should be 2x. And now, we want to deal with this. This is going to be the expected value of x squared plus twice the expected value of x, expected value of y, plus the expected value of y squared. And this is because of independence. And it'll be minus mu x plus mu y squared. So in general, the expected value of x times the expected value of y is not expected value of x, expected value of y. This is where we're critically using the independence assumption. In general, if you take statistics, you'll deal a lot with covariances, with what happens when this is not 0. Alright, so now we just have to finish the end thing. So expected value of x. Well, if we expand out over here, this gives us a minus mu x squared minus 2 mu x mu y minus, having trouble drawing the mu y squared. This is going to be 2 mu x mu y minus 2 mu x mu y. Those terms will cancel. We'll have an expected value of x squared minus a mu x squared. What does that equal?
Variance of x.
The variance of x. And similarly, we'll have a variance of y coming from expected value of y squared minus mu y squared. So this is the proof that the variance of a sum is the sum of the variances if they are independent. If they're not independent, this violently fails. And the formulas become a lot harder. This is why for a lot of the problems in probability, it's much easier to just calculate the expected value, to just calculate the mean. Because linearity of expectation helps us. As soon as we start having squaring going on, we have cross terms. And the cross terms, then we need to know how x and y vary with each other. If we're just summing, so think back to the Happy Meal problem. For something like that, we didn't really have to worry about dependencies. Would it be much harder if we had x plus y plus z? Do we actually have to go through and prove this now for x plus y plus z, or can we get it immediately?
Immediate.
Good. How do we get it immediately?
Set x equal
Grouping.
to.
Grouping. So we just use our grouping, and if we wanted to do it with 3 things, we would do x plus y plus z. And so the variance of x plus y plus z would be the variance of x plus y plus the variance of z, which then, by the early result, is the variance of x plus the variance of y plus the variance of z. So this is one of the reasons I absolutely love grouping, is for many problems, if you can just do the case with 2, you can get any finite case with very little work. Okay, so we've done a lot today in terms of covering material. The next big thing to do is we need one more massively important distribution. So we've been talking about it off and on. I want to just end today with at least briefly mentioning what it is. So what do you think this important distribution that we haven't talked about too explicitly is going to be? The normal. Also called the bell curve, the Gaussian. Anything that has this many names is important. So the normal distribution. And we denote it by mu sigma squared. The density is going to be 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared. We will prove on Friday that this is a probability distribution, that it does integrate to 1. By proof by notation, what is the mean of this distribution? Mu. If mu is not the mean, I should not be using mu in this. What is the standard deviation of this distribution? Sigma. If it's not sigma, I should not be using sigma here. Okay? So the reason that the mean is mu and the variance is sigma squared is not because I've written it like this, but because we can do the calculation. We can do this by brute force. There's a beautiful trick to actually calculate this integral. And we can also use differentiating identities. So we'll tie back into what we've been doing before and go back and show how to attack this using differentiating identities. We will need to use some tricks from multivariable calculus. We will need to learn how to integrate in polar coordinates. Okay.